Recently, a YouTuber called Thunderf00t made a new video about an upcoming series on the universe, in perspective. I posted a comment on that video, which I considered to be an interesting tidbit of information, so to speak. The response I got was rather disturbing, for two reasons. Firstly, the vitriol, which arguably is the less important reason, but the second reason, and the reason that I'm actually making this video, is the lengths people are willing to go in order to debunk a comment using what I could only describe as nonsense physics. A kilogram is a unit of mass, not weight, brackets force. Although pounds is a unit of weight, brackets force, which is kind of weird. But anyway, you can't convert a kilogram to a pound because they are different quantities, brackets mass versus force. You either have to have kilograms or slugs, or newtons or pounds. Slug is the real imperial unit for mass. Now, I will say that in some of the replies to the comments, I have made the odd technical mistake. Although, the physics that I've used in subsequent comments have been sound. So, with that in mind, I'm going to address one of the first objections that arguably has some substance. Now, part of the issue with all this is that pound can actually be a unit of mass. It's ambiguous because the pound can be a unit of mass, as in a pound mass, or a unit of force, as stipulated in this comment. In the UK, in Britain where I'm from, most of the textbooks I use, if they include imperial units at all, which often they don't because imperial units are obsolete in an age where we have Standard International, but if they do include imperial units, they tend to list pound as a force rather than a mass. But without stipulation it could be either. There is an ambiguity here. Now, this would arguably be not a problem if, in Thunderf00t's video, he had always stipulated that he was talking about mass, but this is not the case. Listen to this clip.
You can lose 1 kilo, that's like 2 pounds per day, with no fuss, no tricks, no dieting, just literally breathing the weight away.
Now, it seems clear to me that he was referring to mass rather than weight, although he explicitly did say weight. So this is part of the issue. Are we talking about weight or are we talking about mass? So the ambiguity of the units of the imperial units don't exactly help, because it's perfectly legitimate to use pound as a measurement of weight, whereas it is not perfectly legitimate to use kilograms as a measure of weight. Now, for all those people that are going to start shouting about kilogram force, I'll get to that in a second. But please note that kilograms and kilogram forces are not the same thing. And anyone that thinks they are the same thing is doing something fundamentally wrong. Now, there is a problem here. And the problem is not so much a colloquial one, because when we talk about weighing each other, we're really referring to the mass rather than the weight. But in this video, we are talking about things that could potentially get confusing. Now, listen to this clip.
The Apollo space program. You see, if you're going to put 3 men in a oversized Coke can and fire them off into space for a week or so.
So this context where we are talking about astronauts in freefall, that is to say, orbiting the Earth, a weightless environment, or even walking on the moon where their weight is reduced compared to them standing on the Earth, you can see that this could be a breeding ground for confusion between the terms mass and weight, especially if mass is substituted where weight is implied, or in this case vice versa. From the Wolfram page on units and measures, quote, "A unit of weight in the British engineering system equal to about 4.5 newtons that is commonly used in the United States." That's the definition. Unfortunately, there is a great deal of confusion about the definition of the pound, with many authors using the unit to denote the mass equivalent of about 4.5 newtons, namely 454 grams. The use of the unqualified term pound is therefore strongly discouraged, with more descriptive terms pound mass and pound force being preferred. The confusion between pound mass and pound force alone is a good reason to use metric units wherever possible, and I would agree with this. Now, I know that the avoir-de-pose's pound is used widely without qualifiers, but so is the pound force, that is, the pound force from the British engineering system, and this is definitely widely used in England and even in parts of the United States. Often in science, physics, maths textbooks, the pound is denoted by a unit of force rather than mass. Now, even if it is the case, and I'm not sure it is, but even if it is the case that the avoir-de-pose's pound is more prevalent than the force pound, both terms are still used widely, and this only goes to highlight the ambiguity of using them without qualifiers. So it doesn't invalidate my point at all, although I do concede that it is a possibility that one may be used more than the other, which is something I did not anticipate. In any case, this article offers a solution to the problem. We can either use a qualifier, like specify pound mass or pound force, or we can use, like I suggested, an unambiguous unit like the slug. Or of course, the best solution is to not use imperial units at all. We should be using the standard international system of units. Okay, so I'm going to finish here on the technical state of affairs and move on to the more interesting physics. Now this is the crux of the video, because people were willing to go one step further into the land of madness and try to debunk a perfectly sound physics idea using nonsense. So I will now come to the physics. What is the difference between mass and weight?
Okay, so I'm going to go through some intuitive definitions and then go on to some more rigorous equation building. Okay, firstly, what is mass? Intuitively, mass is the amount of stuff something contains. Now, this isn't the best definition, it's not the most useful definition, but it is the easiest to understand. If I'm holding a bottle and I add some water to it, then the bottle that I'm holding in my hand will increase in mass. Now, mass has a property called extensivity, which means that if you have a 1 kilogram mass and another 1 kilogram mass and you put them together, you get a 2 kilogram mass, which is nice. The masses add together. The total mass is equal to the sum of its parts, which is really nice. Now, finally, in terms of mass, I want to describe something else that mass is. It's something called a scalar quantity. Now, a scalar quantity is something that has no associated direction. If I held a mass up in my hand, like if I hold a book that has a mass of 1 kilogram, that 1 kilogram mass does not have any associated direction. It's meaningless to say that's a 1 kilogram mass west. What does that even mean? It means nothing. It's a scalar property because it has no associated direction, and this is important. Now, finally, before I move on, I want to just describe something that's rather incidental to all this, and that's about units. You cannot say that this mass is 1 or 5 or 7 without giving a unit. I mean, it's obvious that without something to compare it to, these numbers are meaningless, but there is another very important idea at work here, and that is that a kilogram is fundamentally different from a metre. One describes length, one describes mass. You cannot equate the two things. They have something that we call different dimensions. They are not dimensionally equivalent. In other words, you cannot have an equal sign that and then have on each side two properties that are incompatible, like a metre or a kilogram, or a newton and a kilogram, which is part of the whole point I'm getting at here. This idea of unit conservation is important. It means you can't compare things that are not alike in physics. You cannot say that a kilogram is equal to a metre, because even though they have the same number in front of them, that is to say 1, they are completely different quantities. In no universe will a kilogram ever equal a metre, and in the same way, a kilogram will never equal 10 newtons. It's a subtle point, but it's extremely important. You cannot cancel down these two different units because they're just completely incompatible. It's like saying an orange is equal to a pear, or 2 oranges are equal to 2 pears. It just doesn't work. Actually, this is more useful than it is a problem, because it means that if you do end up with incompatibility of units, or dimensions, as it's more formally described as, then it's telling you you've done something wrong, you messed up. It's telling you that you've got an equals sign that isn't really an equals sign. which is actually really useful because everything in all of physics obeys this. So you can use it to check problems. If you're doing a problem that requires a distance and you end up with a speed, obviously you've done something wrong. It's like saying, how fast does your car go? And then you say, it goes at 70 meters. 70 meters? That's not a speed. Okay. And it's just as meaningless to try and claim that 70 meters is a speed as it is to claim that a kilogram is a weight or 10 newtons is a mass. I hope this point is becoming clear. If someone wants to talk more about unit conservation, then I've made a video on this a long time ago. But from now, I'm going to move on and talk about weight and its relation to mass. Okay, so I've done a little Venn diagram here that sort of describes the relationships between these quantities. One key point I'm going to bring up now is that it gets a little bit more complicated because a pound force, that is, the force, the pound that I described in my comment as a unit of force, is not only describing weight, it can describe any force. Any force can be described by a pound force. Or, if we're going to use the obviously superior standard international units, then a newton does not have to be a weight, does not have to describe a weight. It can also describe any arbitrary force. In other words, a weight is a force, always, without exception. A weight is a force, no exceptions. But a force is not always a weight, and there are a zillion examples of this. The thrust that you get from your car, that moves you from A to B, there's a force acting there. Clearly that's got nothing to do with the weight of the car. You could talk about the force between two electrons, and that's an electrical force. Again, it doesn't really have a lot to do with the weight of the electrons. Okay. Where does mass come into all of this? Well, mass is over here. Note that a mass is not a force, and a force is not a mass. These two, like I've said, are incompatible. But a mass and a weight are directly related. They are not unrelated quantities. They're like two peas in a pod, as it were, but they're not the same pea in the same pod. They're like two different peas in a pod. You can get from a mass to a weight by multiplying by an acceleration. Or it doesn't have to be a weight, it could be any force. We're getting here towards Newton's second law, which describes the relationship between a force and the acceleration of the object that the force has acted upon. So there is a link between mass and weight, but they're not the same thing. I think that should be clear. Now, I'm going to want to say one final thing before I get into equation building, and that is the difference between a scalar and a vector quantity. And this is important. Now, in the case of the kilogram masses, this is a scalar quantity, and that simply means that the quantities have no associated direction. A kilogram doesn't act in any direction. That's meaningless. It's a scalar. You can just add them together like numbers. 1 plus 1 equals 2. 2 plus 3 equals 5. These kilograms behave in the same way as numbers. 1 kilogram plus 2 kilogram equals 3 kilograms. Everything behaves nicely. You can multiply them like you can multiply numbers. Everything's fine. But some quantities in physics have a direction associated with them, and this is called a vector quantity. Now, a vector quantity can be described by a magnitude and a direction. And this is the case with forces, and of course by extension weights, because a weight is a force. Because of this, you cannot add them. So here I have two forces. I've got a 4 Newton force and a 3 Newton force, and I want to describe the sum of these two forces, and it's actually 5 newtons. So in this case, we've got 3 plus 4 equals 5. It doesn't obey this sort of simple law of addition that our kilogram masses did. And this is part of the reason why it seems entirely ridiculous to try and equate something like this with a mass, which behaves nicely with respect to addition. Now, it turns out that forces behave something called vector addition, and the observant among you might notice that this is actually a Pythagorean triangle, and that 3 squared plus 4 squared equals 5 squared. You can describe the magnitude of a vector in this way. Vectors add using a process that you might call from tail to head. So if you want to add two vectors, this vector and this vector, the way you do it is you start off here and then trace to the head of this arrow, just like joining arrows together. So if you have any arbitrary number of arrows that are joined together, you can find the total arrow by joining the tail of the first arrow to the head of the last arrow, and that'll give you it. And in this case, you can just use Pythagoras' theorem to work out the magnitude. This is the magnitude, the number, the distance, if you will, along the arrow, the distance along the arrow, the vector. Okay, so it's important to note that a force is not just 5 newtons. 5 newtons is a force, but it's got another property. It's got this vector property, which means that you have to specify which direction you're talking about. Is it 5 newtons west? Is it 5 newtons east? Is it 5 newtons towards the centre of the Earth? In the latter case, you might be talking about a weight, because weights, in the usual sense, do act towards the centre of the Earth. So, I mean, with a weight, you don't have to worry about this so much because all the arrows are pointing in the same direction. So, of course, they will behave a little bit more friendly. It will behave in a more friendly way. But with forces in general, which is described by something like the force pound, you have to be very careful about this sort of thing. So you don't just have a number and a unit, you also have a direction. And if you remove the direction and just talk about the number, then that is called the magnitude in the absence of a direction. Okay. So you can actually describe something called the magnitude of a force. So the magnitude of a force is the force, but without the specification of the direction that of the force is in. I mean, that's still a perfectly acceptable physical quantity. And you can have equations that work in vectors and in scalars, but it's not giving you the whole information. Mass is always scalar, whereas force is a vector quantity that you can, if you want to, describe as a scalar. But it's not advisable because if the forces are not acting in the same direction, you'll come up with problems. Okay, so now with this background in mind, I'm going to go through some equations.
What you're saying here is the special property that mass brings to the party when we're talking about inertia, it's like reluctance to move, is exactly the same as what it brings to the party when it starts interacting in gravitational fields.
Yeah, at least within a constant of proportionality, which you can always hide in that big G, but they're basically measuring the same quantity. And that equivalence really just follows through into this equivalence, which then leads to the whole of general relativity.
Okay, so this was a clip from a 60 symbols video that people tried to use to debunk my point. Now, it should be obvious from what I've already said that mass and weight are not the same. They don't have the same units. But the clip that I've illustrated is a very important point, and I find it really interesting, and I would advise people to watch the whole 60 symbols video. So now I'm going to explain exactly what that video was about, and try and describe the source of confusion that people had over this video. Although I suspect some people just read the title and thought, let's read the title to debunk a comment. For the people that did that, please don't. Please actually watch the full video before doing something like that. But anyway, what is the definition of mass from a mathematical point of view? Okay, so we can describe mass in terms of its inertia, in terms of the inertia of an object. So, if we're trying to accelerate an object, it might be a car, for instance, and we have a force here, so I'm going to call this the force that's causing the acceleration. And notice this is underlined because it's a vector quantity. That's what the underlining means. Okay, so the force causing the acceleration is equal to the mass of the object multiplied by the acceleration that the object will then go on to do. Now, you can simply rearrange this formula and have force that's causing the acceleration divided by the mass is the actual acceleration. And from this, you can see that the mass is actually inversely proportional to the acceleration. So that is to say, if you apply the same force to two objects, an object that is twice as massive will only have half the acceleration, because there's an inverse proportionality going on here. So, in other words, we can describe the mass of an object as its reluctance to move, or its reluctance to be accelerated. Now, that's one definition. The other definition is the gravitational definition, and this is described here. Now, what we have is actually Newton's law of gravitation written here. Okay, so this is the gravitational force that's acting on an object in the presence of a gravitational field. Okay, so what is this force equal to? Okay, so the gravitational force on an object in a gravitational field is equal to, so I've got some constant here, g. That's a fundamental constant of the universe, the gravitational constant. We've got this big M, which is actually the mass of the object that's causing the gravitational field. I don't want you to worry too much about this big M, because I want to think more about the mass in the presence of the gravitational field, rather than what's actually causing it. We've got r squared term here, which is the distance of the mass from the source of the gravitational field. So in the case of the Earth, this will be the distance of the mass that we're thinking about to the centre of the Earth. So we've got r squared here. This thing here is a vector. This is actually called a unit vector, and this is tagged on just to make sure that this equation is a vector equation rather than a scalar equation. Don't worry about this too much. It doesn't actually add anything to the magnitude. It's just a unit vector, like the number 1 in vector form. And then m2 I've written here, which again is the mass of the object in the gravitational field. Now, the interesting thing is that, of course, this gravitational force is just like any force. It can cause acceleration. I mean, this here is Newton's second law. This force can be any force. Any force can cause an acceleration. All forces cause accelerations. That's the whole point of a force. This is Newton's second law. So, of course, this gravitational force can cause an acceleration too. So there's absolutely no reason why we can't equate this to this, because it's a force, it can cause an acceleration. Bear in mind, even if the mass equivalence principle was not true, we would still be able to do this. Okay? That's not the point. Equating these two things is something we can do anyway, because forces cause accelerations. That's Newton's second law. Okay, so this is what we've done. We've equated the gravitational force, which is equal to this thing that I just explained, is equal to a mass times an acceleration, and we've got m1 here because this is the sort of mass that's causing the acceleration, the reluctance to move, the inertial mass, as it were. Now, the key point here, the mass equivalence principle says, and there's no reason why this should be true, but in our universe it is true, that this mass m1, the inertial mass, and this mass m2, the gravitational mass, just so happen to be equivalent. Now, I'll just point out that when people say gravitational mass, sometimes they're talking about gm2 rather than just m2, and that's completely understandable because we're talking about a proportionality constant here. This is just a constant. It doesn't really matter. The point is that if we double m2, then this gravitational force is going to be doubled. But for the sake of simplicity, I'm going to define the gravitational mass as being m2 and the inertial mass as being m1. So anyway, we've ended up with this here. And the key point behind the equivalence principle, which is the crux of the video, is that m1 and m2 are actually the same thing. And there's no real reason why this should be the case. It just so happens that it is the case. It's a rather remarkable fact that just happens to be true. But if it is the case that m1 and m2 are equal, then we can cancel them. Nothing wrong with doing that. And then we get this equation. We get the acceleration, which is the acceleration here, the acceleration caused by the force, which is the gravitational force, the acceleration due to gravity, the acceleration due to gravity now, is equal to this thing. And note, this thing does not depend on the mass of the object. Now this is what Galileo discovered, that regardless of the mass of the object, they will all fall at the same rate. If you drop a feather and a ball bearing, they will both hit the ground at the same time, negating factors like air resistance. So we end up with the acceleration is a function that is not dependent on the mass. It's dependent on things that, like the mass of the Earth, which is, you know, got nothing to do with the mass of the object that we're talking about. And we've got this r² factor, of course, that's still there. So, key point, acceleration due to gravity is not dependent on its mass, on the mass of the object that's being accelerated. So, in general, the mass equivalence principle. Now we've basically gone through how objects fall at the same rate, regardless of their mass, and how mass is defined in terms of a gravitational force. But you can do something similar with the mass of the Earth, or not the mass of the Earth, but the gravitational field that an object produces. In other words, the mass equivalence principle is that the inertial mass is proportional to the passive mass, the passive gravitational mass, and the active gravitational mass. So that these two different masses, one is the gravitational force that's acting upon the mass, and one is the gravitational force that the mass produces. So this is the mass equivalence principle. In other words, these three sorts of masses are basically the same. There's no real difference between them. They're all proportional to each other. And this is the key point. If you double the mass of an object, you double its reluctance to move, you double the gravitational field that the object emits. Emit is probably not the best word to describe, but you double the gravitational field that it produces, and you also double its affinity to a gravitational field. So, all these masses are basically the same. And note, of course, that the fact that you double its affinity for the gravitational field and its reluctance to move, these two factors sort of cancel each other out, and this is why we end up with all the masses fall at the same rate. Okay. Okay. So, let's look at weight now. So the definition of weight that I'm going to use is that weight is defined as the mass of an object multiplied by the acceleration it feels due to gravity. And we've derived the function for the acceleration due to gravity here, and if we substitute it in to what g is, we restore Newton's law of gravitation here. In other words, we're saying weight is equal to the gravitational force felt by an object. We're defining this F here to be weight. Now, of course, if you double the mass of the object, the gravitational force is also going to double. In other words, we can say in a sense that the gravitational force, or the weight of an object, is proportional to its mass. But we can't say that both are equivalent, because you can see the weight of the object depends on so many other factors as well. Well, actually two other factors, but you get the gist of this. It depends on the mass of the object causing the gravitational field and the distance from that object. Of course, fits in with Newton's second law rather well, because the gravitational force is perfectly capable of causing an acceleration, just like any other force. and it's this acceleration that an object feels when dropped in the gravitational field of, for example, the Earth. So, simply put, weight is the gravitational force an object feels, which is a vector, pointing towards the centre of the Earth in most cases. Now note, we can often define g to be about 9.8 newtons. Sorry, we can often define g to be about 9.8 meters per second, because if you don't go far away from the Earth, these factors here, namely r and, of course, m doesn't change at all, don't change. So we can say that g is approximately, functionally, 9.8 meters per second. Of course, there are problems with this, because the gravitational acceleration does actually vary on the Earth. At the equator it's about 9.78, and on the poles it's about 9.82 meters per second. So there is a variance due to latitude. Obviously, the further away you are from the centre of the Earth, the weaker the gravitational acceleration is as well. So g does vary, but operationally we can often say when working with stuff on the surface of the Earth, it doesn't vary within the distances we are using, so we're just going to call it 9.8 meters per second. But note, if you want to call all this stuff here 9.8 meters per second, that's fine, but you still have to multiply your mass by 9.8 meters per second. You can't just say that mass is equal to force because of this. No, mass multiplied by your 9.8 meters per second is equal to the force. You've still got to multiply by that 9.8 meters per second. And notice that unit there. You've got to have the unit in as well. Okay, moving on. Now you'll notice that I've got an upward force as well. This should be there for an obvious reason. Obviously, the object is not accelerating when it's just sitting on the Earth, so we need a contact force, a force that acts in the opposite direction. This force is the normal, or the contact force. It stops the object from accelerating. So from that, we can deduce that it must have the same magnitude, but act in the opposite direction. In other words, these two forces add up to make no force. This force is acting in the opposite direction to this force, so the vector sum of the two forces is 0. So the object doesn't move. Now, it turns out that when you're using a weighing scale, when you want to work out your weight, it's not just as simple as W equals mg, not just as simple as the gravitational force. You have to look at this contact force a little bit more, because it's actually the contact force, not the weight, that gives the impression of weight. Under the definition of the weight that appears to you as a number on your scale, it's the contact force that produces it. It's actually the stress on your body due to this contact force that gives the illusion of weight. This means that even if the gravitational force is acting upon you, you can still feel weightless, because there might not be any contact force. So, if you're falling from a plane, say skydiving, if you're in freefall, you could feel completely weightless, because there's no contact force. Even though you actually have a weight, you feel weightless. Now actually, some people define weight to be that thing that you see on the scale, and that's rather more nuanced because of things like freefall. Under that definition, when you're freefalling, you have no weight. Although, of course, a gravitational force is acting upon you. It's that whole confusion about there's no gravity in space. And a lot of people don't understand this. The feeling of weightlessness is due to the absence of a contact force, not due to the presence of a gravitational force. So another way of defining weight is the magnitude and the direction acting towards the centre of the Earth, for instance. Or we could just define it as a scalar quantity. We could just say weight, under this definition, is the scalar quantity that is the magnitude of the contact force. And this definition would work for things like standing on the moon, standing on the Earth, and being in freefall, where you're weightless under that definition. So there's basically two definitions. We can use the simpler one, which is just the gravitational force, or we can use the one that produces the number on the weighing scale. Now, I'm going to introduce the concept of g-force now, which is about this so-called apparent weightlessness. Now, you can also you can say that weight is only felt as forces that do not produce weight is only felt as forces that produce proper acceleration. Gravity does not produce proper accelerations. A proper acceleration is essentially an acceleration due to anything except gravity. This is sort of a difficult concept to get your head around, because it also implies that your weight is due to the forces except the force that causes your weight. It sounds sort of contradictory. The definitions sort of get rather difficult to pick apart. So this is the whole concept of weight, in a sense, is redundant, and you can see why mass is a far more useful quantity. I mean, because of all these things about apparent weight due to gravitational forces, things get rather difficult to avoid the confusion between these two things. So mass is a far more useful property anyway. Now, returning to this, g-force. Now, g-force is something that you feel when you're accelerating. When you're on a fairground and you're on a wheel or something, you will feel the g-force. Now, g-force, even more confusingly, isn't actually a force, it's an acceleration. When you say 1g, of course, g is an acceleration, not a force. G, for instance, might be 9.81 meters per second. So, the contact force, measured as an acceleration, a proper acceleration, that is to say, an acceleration that is not caused by gravity, is 1g. So the contact force is 1g. In other words, when you ignore all improper accelerations, you end up with an acceleration that's trying to lift you off the Earth at 1g. That's a proper acceleration. At 9.81 meters per second, and that is the contact force that's producing this 1g of g-force, which is actually an acceleration when ignoring gravity. So we get to this sort of stage where a proper acceleration is defined. Simply put, I mean, it's not quite as simple as this, but a proper acceleration is defined as an acceleration that is not due to gravity. Now, this is where the 60 Symbols video started to go into sort of the concepts of general relativity. If we imagine an elevator, I've drawn two elevators here. I've got one elevator that's accelerating up at 1g. The g-force is 1g, it's accelerating upwards. We have another elevator that's sitting on the Earth. It has a gravitational force, or the weight under the first definition, of mg. How can you tell whether you're in the elevator accelerating upwards at 1g, or the elevator sitting on the Earth under the gravitational field? And the answer is you can't. And that's the crux of this general relativity thing. It's impossible to tell whether you're accelerating or whether you're under the influence of gravity, because your weight feels the same. And this is the whole issue about weight being with respect to an inertial observer. In other words, with respect to someone that's in freefall. We measure weight with respect to someone that's in freefall. Someone in freefall would measure their weight as being 0 newtons. So someone accelerating upward in an elevator at 1g would measure their weight to be, I don't know, what's the typical mass? So 50 kilograms multiplied by 1g. I don't know what that is. That's about, I don't know how many newtons that is. But let's say someone has a weight in this elevator of 100 newtons. In this elevator, they would also have a weight of 100 newtons, as measured on the scale. So this is the whole point of general relativity. You can't tell you can't tell an acceleration from a gravitational field. Both feel the same. And this is where we start to describe gravity as being actually a curvature in space-time, and that a gravitational acceleration is different to other forms of acceleration. And this is the whole concept of proper accelerations versus improper accelerations. Okay, I hope I've tried to explain that, but to sum up, a mass is a scalar extensive quantity that is invariant. Doesn't matter where you are, doesn't matter what field you're under the influence of. It could be an electric field, it could be a gravitational field, it could be any field. Your mass doesn't change. Your weight is a force, and under the simplest sort of definition, a weight is just the gravitational force acting upon you, which does vary according to your mass. Weight and mass are linked. I went through that with the flow diagram at the beginning, but they're still completely different things. One is an extensive property that is scalar, and the other is a force, which is a vector. I hope I've tried to go through a few things that people sort of misunderstood. The concept of things like g-force and apparent weight are rather difficult to get your head around. So it's fair enough to simply define weight as being the gravitational force you feel due to gravity. So of course, someone in freefall would still have a weight. But that's fine. Thank you for listening.